Start recording. Okay, so today we are going to continue our discussion of Monte Carlo approximations. Now, to remind you, Monte Carlo approximation says, hey, this game or this scenario is too difficult to analyze statistically. So let's not do that. Let's just count the outcomes and see how often we have outcomes. I have posted quiz 5. It will be due at the end of the month, by the way. So quiz 5 will be due March 31st. Okay. And that one is on dictionaries. 1 second. I have got two-factor authentication that needs to happen. Answer. Okay, and I have to do that every 2 weeks. Okay. Now let's go ahead and wrong class. Python. All right. So what we're gonna do is again, and yeah, we're a bit behind in what my scheduling was, but that's fine. We're going to continue doing Monte Carlo approximations and cheating at statistics. And we're going to, what we're going to do is that we are going to work on this Monte Carlo simulation. So you can find the link here. I'd been planning on doing this last Thursday, but instead I went over the homeworks. So, you can find this by going to your Runestone. It's by either going to Zoom, going over to Canvas, clicking on Module 9, and scrolling down to the bottom and click on this, or go to our Runestone course and going and clicking on Monte Carlo simulation, number 12. All right. So, and we're not going to go in order with this one. There's 3 exercises here. I'm just going to do the second one. I find to be very interesting. I think you might find very interesting for a final for kind of what you might want to do for a final project. If you're into stock prices and trying to predict stock prices, that's one aspect of Monte Carlo approximations you can do. So, but we're going to start off with the Monty Hall challenge, which is at the bottom. Okay, so the idea here is so the Monty Hall problem is a simplification of the game Let's Make a Deal. Okay, and so we have the idea here is that if we pull up our whiteboard. The idea here is you're contestants in this game, okay? Yes, we were doing Hangman in another class. So we're doing, okay, there we go. So we've got ourselves 3 doors, 3 secret doors, okay? Door 1, door 2, and door 3. Right, and I can go ahead and put a knob on each of them. Okay. Now, and the idea here is behind 2 of these doors is a goat. Typically, when we present this, it's a goat. And behind the other door, the door that doesn't have a goat behind it, is a car. And the idea here is that you're going to choose a door and you're going to get whatever prize is behind it. So you've got a 2/3 chance of getting a goat and a 1/3 chance of getting a car. Now, and the assumption here, at least when it was proposed, when this problem was proposed, is that the car is a more desirable outcome than getting a goat. I know that there are some among us who like, well, I don't need a car, but I could certainly use a goat. They're so cute. You know, they jump on stuff and they climb and they eat everything. Cute. But the assumption here is that we want to try to get the car. So just right off, if I choose something, all right, if I choose a door, I have a 1 in 3 shot in getting that car, right? A 1 in 3 shot in getting. Everybody agree that? Like if I simply am just going to choose something and get whatever's behind the door, there's a 1 in 3 chance that I get that I've chosen the car. Okay. So the twist is, let's say I choose door number 2. Okay. Now Monty here, the host of the game, is going to do something. He's going to open one of the doors. Specifically, he's going to open the door that does not have a car. He opens one of the doors to reveal a goat. So say he opens door number 3 and reveals that there's a goat there. Okay. Now, here's the question. So, he gives me the opportunity to switch. Should I take it? And that is the question. Yes. Yes, I should take it. You should always take that opportunity. And it turns out you should always take that opportunity to switch. Okay. But the reason why drives so many people crazy. Okay. Because the reason is, okay, I've got, and your logic might be, okay, if I switch, I've got even odds, right? There's 2 doors left. It's got to be behind one of them, right? So if I stay with this one, it's even odds. If I switch the other one, it's even odds. But that's not the case. Your chances of winning if you switch are actually 2/3. And that is the Monty Hall paradox. The idea here is that if I switch, I have a 2/3 chance of winning. And this was the subject of a minor, quote unquote, I don't know, like if Twitter was around, it would have been a Twitter storm or a tweet storm or something, you know, but there wasn't. Instead, there was Parade magazine. Okay. So, right. Instead, we had Parade magazine. And the idea here, so let's take a look at the Wikipedia page. So it was so it was originally posed to and solved in a letter in the American Statistician in 1975. No, nothing exciting then. But it became famous as a question when a reader, Craig F. Whitaker, wrote into Ask Marilyn, to Marilyn Vosavant's column in Parade magazine. Suppose you're on a game show and you've got given a choice of 3 doors. Well, behind one door is a car, behind the other goats. You pick a door, say number 1, and the host, who knows what's behind the other doors, opens the door and says, not say number 3, which has a goat. He says to you, do you want to pick door number 2? Is it advantageous for you to switch? And Vosavant's response was that the contestant should switch to the other door, and saying, understand assumptions, the assumptions that you wrote down, switching gives you a 2/3 probability. Specifically, the assumption is that if you pick one and then he opens one and he reveals a goat, then you want to switch. Well, if you remain with your initial choice, you only have a 1/3 probability of winning. Okay. So these are all about given probabilities. And what kind of happened is that many readers of Vosavant's comments refused to believe that switching is beneficial and rejected our explanation. After the problem appeared in Parade, approximately 10,000 readers, including nearly 1,000 with PhDs, wrote to the magazine, most of them calling Vosavant wrong. Even when given explanations, simulations, and formal mathematical proofs, many people did not accept that switching is the best strategy. Paul Erdos, one of the prolific mathematicians in history, remained unconvinced until he was shown a computer simulation that showed how that would work. The problem is that this is a paradox of the veridical type, because Vosavant's solution is so counterintuitive it can seem absurd, but it's nevertheless demonstrably true. So the idea here is that you've got, now why is this? Well, we've got a couple of different scenarios that can happen. Okay. So suppose you're always picking door number one. Okay. If you pick door number one, okay, that's equivalent to picking any other door. Okay. Which door you actually pick as your initial one doesn't really matter. Okay. So I could easily say, suppose we pick number 1, 2, or 3. They're mathematically equivalent. So there's 3 possibilities for me when I pick door number 1. Okay, from top to bottom. So this is scenario 1. I pick a goat. Sorry, the one I initially pick has a goat behind it. Monty opens up door number 2, which has the goat, and so the car is behind number 3. I switch and I win. Scenario 2, goat number 2 is over here, or it doesn't matter. A goat is behind here. They're interchangeable. I have a goat on. I have a goat. So first goat, second goat, switch, and he opens up and reveals, switch, and I win. Okay, because he's always going to reveal goat. Third possibility, right? Because there's a 2/3 chance my initial choice is going to have a goat, right? Because there's only 1/3 chance initially I'm going to pick a car. Okay. Regardless of what I do, if I initially pick the car, if I switch away from it, I'm going to lose. So we can see these are the outcomes, right? These are the outcomes. It all relies on the fact, and this is the key point, that what Monty is revealing is a goat. It's never not going to be a goat. Okay, he's never going to reveal the car. Okay. Okay. Another way I like to think about this, or the way that really got me think about this easily, is by generalizing this problem. Suppose we have 1,000,000 doors, okay? And behind one of those doors is a car, and behind 999,999 of those are goats. And that probably has some kind of unimaginable smell, or noise with that many goats. Okay. So it's the same principle. I choose a door. I've got a 1 in a million shot of winning, of getting the car, right? Monty then opens up 999,998 doors. In other words, all of the 1,000,000 doors, but the one I chose, and another one. And he reveals that behind all those 999,998 doors are goats. Should I switch? And the answer is yes, of course, because when I initially chose, I only had a 1 in a million chance of getting it right. So I'm basically betting against basically what I'm betting is, was my initial choice wrong? And there's a 999,999 out of 1 million chance that I was wrong. So I'm gonna switch. This is just kind of so that takes it to its kind of it's kind of it's what you call it. It's absurdity. Now you can directly calculate this in statistics using Bayes' theorem. I say that having not done that in a while, but basically that's the probability of A given B. That's what Bayes' theorem is. But as you can see, these math equations look mildly scary, and honestly, this is not a statistics class, and that's not what we're trying to do. And besides, statistics aren't necessarily approachable for everybody, right? It's not, you have to have a necessary background. But showing somebody this is how the game is going to work and running it, we'll do this. So we'll do a Monte Carlo and we'll show basically what the strategy is, okay? So with some Python code, we can use a random number generator to put a prize behind a door, then use the remaining random number generator to let the contestant pick a door. Okay, then you can simulate what's going to happen. You know what? We're going to use random. We're going to use some new functions in random that are going to make this a lot easier and a lot easier to read too. Specifically, what we're going to use is random.shuffle and random.choice. Okay, which are two of my favorite things. So what I'm going to do over here is I'll start by importing random. Okay, import random. Okay, and now what we're going to do is that I'm going to write basically we're going to write a game. And we're going to start, and we're going to just put down like ideas of what we need for the game. Okay, first off, we need that initial configuration. We need the initial configuration of our, and this function is just going to simulate a single game and tell us what the result is. Does that make sense? And then the idea here is that we simulate the game, we run it, and then once we are satisfied that the game is working, we can then simulate it a bunch of times. So first off, we need the doors. And I'll just do that as a list, right? Because, and I'll show you why in just a second. But, well, I'll show you why by doing it. Because if I store it in a list, I can basically have 3 items in the list. Specifically, I can have goat, goat, and car, right? Can have it nice and, or I could also do capital G, and C, but honestly, right, we're working in text, in a text editor, so we might as well use the text so that's readable. Okay, so we have doors, we have goat, goat, and car. Now, every problem should be different. So what I'm going to use is a function from random, random shuffle Python. And I'm just going to pull it up in the docs to make sure that it's correct, but also just to show you, but also to show, just so I can have this page pointed up. All right, so what we have, oh, and there's choice, so we'll show you, shuffle the sequence X in place. All right, and it says, hey, so it will, and it uses something called the Mersenne, let's see, twister to do all the random stuff. But anyway, shuffling, what that does is that will put that in a random order for us. That makes sense? It's very, very useful. So if I do doors, so if I do random dot shuffle doors, and then I print the doors, I'll be erasing that print statement in a second, but what I'm going to do now is I can call the game and I can test, hey, we're shuffling this. Goat, goat, car. Goat, car, goat. Everybody see how it's coming up with a different configuration each time, right? Now we're going to get some long stretches sometimes where basically maybe it's unbalanced, but statistically speaking, the random number generator is statistically balanced, meaning it will, that car will show up basically wherever it needs to show up. So it will show up in all the places approximately equal amount of the time, given a long enough streak. Okay, so that's what we are going to do. All right. The next thing we're going to use is we're going to need a, rather than making 2 functions, I'm going to do something a bit different. Maybe I'll take in a single function and like have a strategy. And we can choose between 2 strategies. Regardless of the strategy, what we're going to do is we're going to say our initial selection is going to be what you call it, is going to be door number 1, or in other words, index 0. I'll call them 0, 1, 2 from now on. So I'm going to open up door 0, right? As I'm always going to pick door 0 as my initial choice, because statistically that's what matters. And that doesn't really matter for us to keep it down, but we might take it out later. Initial choice is equal to doors 0. Oh yeah, you're going to be doing something that involves random on the final, definitely, because you'll be doing a Monte Carlo approximation as one of your questions on the final. I'll be giving you a very simple game to simulate. Okay. doors, 0. So we've got goat, goat, car, random nut shuffle doors, initial choice. We grab our initial choice. Now, what we do depends on our strategy. So let's go ahead and say what our strategy, let's go ahead and then pass in the strategy, which is, and then we'll pass in a string to say what our strategy is to test that. Does that make sense? So I'll have like, if a strategy is, if strategy it equals stay, do this. And then L if strategy is equal to switch, we're going to do this instead. So that allows us to test different things. Make sense? Okay. So what we're going to do now, so if the initial choice is stay, then here's what's going to happen. We can fully simulate what's going to happen, right? Revealed is equal to, so basically what's going to happen is that we are going to reveal one of the two things that are one of the two doors. So if door 1 is a goat, then actually we don't really need to do much for the strategy say, but basically what we're going to say, revealed is equal, I'm over engineering this, reveal is equal to goat, and revealed if door number 1 is that, then we are going to say revealed is equal to, yeah, we don't need this. We just, if our strategy is say is stay, then our choice is made, right? No matter what happens. So we can just simply say that, hey, if door 0 equals a car, print win and doors. And I'll show what that is. Now, if our strategy is switch, then that's where it gets a bit different. Okay. If strategy is switch, then we can basically say, hey, we could easily just simply say if doors is not equal to car, right? If doors is not equal to car. But let's go ahead and actually simulate this. Basically, what's going to happen is that if doors 1 is equal to a goat, then Monty will reveal it. Revealed is equal to doors 1, and then choice is equal to, we're going to go ahead and swap and switch. So I'll say swap is equal to doors 2, else, yeah, it's the other ways around, which is that what gets revealed is, and again, this is over engineered, but I just wanted to kind of belabor the point. Revealed And we're going to go ahead and just simply create these as empty strings so that they'll exist out in this block. So else, if else, and now what we're going to do is we are going to print, if swap equals car, print, oh, we'll do the same here. Print win doors, else print booze. All right. So, and the same thing over here. We'll put in the else block over here. Again, this strategy for switch is a bit over engineered because I could just simply, I don't need to specify which is the revealed one, but we can see, so now I'm running with the stay strategy. So I stayed on the goat, I stayed on the car, I stayed on the car, stayed on the goat, I lost. I won because I got the car, right? But now if I change the strategy to switch and I start playing, win, I switched to the away from the goat. Win, I switched away from the goat. Lose, I switched away from the car. Win, I switched away from the goat. And we seem to get more wins than losses. So now that we've got this working, what we're going to do is rather than printing out our victories, what we'll do is that we will return true if we win. I'll return true for winning or false for losing. Which can actually just be simplified into just returning this entire, but that's okay. Okay. Similarly, what we'll do over here is that I will return true and a false. Okay. And now I actually need to print out what I'm doing. So I've got a game and now it's going to tell me, did I win? Else, oh, return false. Wasn't returning anything, so it was giving me none. So can run a bunch of times. So, but that's just not really, clicking this a bunch of times doesn't really give me what I need. So what I'm going to do is now I'm going to simulate this a bunch of times. So I'm going to say trials is equal to 10,000, which is the number of games they suggested doing this. So we're going to run this 10,000 times. And we're going to count the number of times we win. So we're going to do this 10,000 times, count the number of times we win. So far, we haven't played yet, so the number of times we've won is equal to 0. For blank in range trials. So we're going to do this 10 trials number of times, 10,000. If game, we're going to use the strat, and what we're going to do is we're going to put in strategy over here, and we'll create a strategy over here as equal, so we can just change it over here as equal to switch. Okay, if game strategy equals true, wins plus equals 1. We don't have to keep track of the losses, right? Because what our win ratio is going, what our win are we going, what we're going to just simply say is that print strategy, the strategy wins, and now we need to calculate what the win percentage is, which is going to be wins divided by trials. Of the time. Sorry. So there we go. The strategy, so this strategy wins that many times. So now we run it. It says, hey, the switch strategy wins 66.8% of the time, 89% of the time. I'll share it in a minute. And then if I change the strategy now over here to being, what did I say the other one was? Stay? Yeah, if I change it to stay, the stay strategy wins 0.324, so it wins only a third of the time. So let me go ahead and share that code with you. Now I'm not really sure what with Vosavant, like why she got so much backlash from this column when it's been a long solved problem, like it had been solved 15 years ago, although I have my suspicions as to why. But it is one of my favorite kind of statistical paradoxes, of which there are a number. Another one that I enjoy is the birthday paradox, which is that I can say pretty much with confidence that there are two people in this room that share a birthday with each other, right? And you think that's weird because there's only 365 days. So each individual person has only 135, possible, well, 366 technically with February 29th, but there's a lot of pairs of people because we're asking if two people share a birthday. A lot of pairs of people. So let's go ahead and now see a Monte Carlo in action in both a more abstract form, but also a more easy to see form. We're going to do so by approximating pi, and then if we have time left, we'll address the birthday paradox. And then on Thursday, what I plan on doing is I plan on going over some of the some scam games. So games that somebody might attempt to scam you with. Yes. I have shared it. I've clicked the share code button on this. So if you reload your page, you should be able to share. So share code. And then what you'll want to do is after you reload the page, did you click load history? Try clicking load history. Really? Weird. Oh, it didn't give me the whole text of, hey, this code was successfully shared with everybody. Interesting. Okay. I will just post it here and on the Zoom chat, and I'll also post it on Discord. And then also we'll have this entire, wow, you're taking a really long time. Okay, so let's see. Go to Discord and there we go. Post it into Discord. I'll keep it. I'll keep this up. I'll try to get to you later. So let's move on. So we've learned about, so earlier in the semester, we approximated pi by doing a bunch of addition, okay? Right, and we did this whole Leibniz formula where we calculated pi over 4, right, by adding a successive series of fractions, and we got closer and closer to pi. We've done that, but much more fun is doing a Monte Carlo simulation. And I actually did this as part of graduate research. It's actually part of one of those things that it's a example of a problem you can distribute and can be performed by multiple distributed processors, and then that you can tally their results together. So it's a very simple kind of problem over here. And the idea here is that we are throwing darts on a dartboard, okay? The idea here is that, in a whiteboard, is that we're gonna go ahead and, so we have, let's go ahead and see, can I draw a shape? Let's see. Into shape, yeah, I can, nice. All right, so suppose I am drawing, so suppose we have this circle. Okay. That is our dartboard. Make sense? We have some dartboard over here. That's our dartboard. Okay. And the idea here is this dartboard is enclosed in, and let me try to do this a bit better. Shoop. It's enclosed in a square. And yes, I need to make it just slightly bigger. I had been hoping that this would be easier than I thought it would be, but apparently not, because I wanted them to overlap. Okay, new plan. Turn that off. And just and I'm going to freehand this. And you're all just going to have to suffer. Okay, so the idea here is that we've got let the square be defined as our playing space. If I throw a dart, it's going to land. If I throw a dart, it's going to land somewhere in this playing space. It can land here, or 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 here. Right? It can land anywhere in this space. Make sense? If I'm throwing a dart, okay, and just assume that like me throwing it outside of this bound, that's not a possibility. Let's assume that basically that this is a wall, okay, and this is a giant dartboard on the wall, okay. So unless I'm a stormtrooper, I should be able to hit this, okay. Okay. So the idea here is that we can believe it or not, use this to calculate pi. How? Well, we're going to do is that basically we can we can figure out how many darts land on that dartboard. Okay, and then the rest is actually just a matter of math. Yeah. All right, so what about that math? So over here, basically, we've got, that's going to blend in too much, so we'll go ahead and use red. So let's assume that this is a unit circle. What does that mean? That means that it has a radius of 1, okay? If this has a radius of 1, then that means that this square that the side of this square, okay, is 2, right? Make sense? Everybody follow? So let's just do some, we're going to do a very basic calculation of the circle on the left and on the square on the right. Very, very basic, okay? So the square on the left the circle on the left is a unit circle. Now, what is the area of this thing? The area of a circle is pi r squared, right? Pi r squared. So this becomes, so plugging and chugging with a unit circle, by the way, is super easy, right? 1 squared is 1, So the entire area of the circle is pi. Assuming I can spell circle, which apparently is a challenge. All right. So what about for this? What about a square? A square's area is the length of a side squared, right? So its area is going to be s squared, which is equal to 2 squared, which is equal to 4. Okay. Which means that 4 was really funky s square area. All right. So the idea here is that if I take the number of darts that land, now all the darts that land inside the, so if I take the ratio of the circle area to the square area, that's going to be pi over 4, right? Which is interesting. Now here's the trick. If I'm randomly throwing darts at this thing, and this time I'll use, let's see, use sky blue for this one. Sure. If I'm throwing darts, they land places, okay? Then the darts that land in the circle, we could do the darts that land inside the circle. And then every dart that we throw is going to land in the square. Okay? It could be circle darts divided by the total number of darts thrown. Okay? So ideally, if we throw enough darts, the circle darts up here should be, the circle darts divided by the darts thrown should be equal to the ratio of pi over 4. Okay? So because if I throw enough of these darts, then quite a number of them are going to land inside the circular area, and all of them are going to land in the square area. So the ratio of the number of circle darts, the number of hits we got divided by the number of total darts thrown is going to be pi over 4. Because that's the ratio of the circle to the square. Make sense? So so what I'm saying is, long story short, to calculate pi over 4 using this dart strategy, then what I need to do is throw a dart and then calculate, as I just need to throw these darts, count up my number of hits divided by my number of tosses, multiplied by 4, and I get pi. Because why multiply by 4? Because we had pi over 4. Okay, so how do we do this? Well, what we can do over here is that we're going to use Turtle to make this a lot more fun. Okay. Specifically, what I'm going to do is I'm going to use a function in Turtle. I'm going to let this be 0, 0 on the Euclidean plane. In other words, our typical 2D graph, right? And this corner over here is going to be 1, 1. Make sense? And this corner over here will be -1, -1. Make sense? So what I'm going to do is I'm going to use this win set world coordinates function from Turtle. So Turtle docs, and let me just look up a reminder of how to use that. World, set world coordinates. So what I need to do is just simply call, so first off, let's just start out by doing that. And you're probably wondering, what in the world are you doing? But that's okay. Import Turtle First thing I'm going to do is do turtle dot set world coordinates. And what I'm going to do is and it takes in 4 arguments: lower left X, lower left right, Y, upper right, upper left. In other words, these things I just did, the lower left coordinates and the upper right coordinates. So -1, -1, +1, +1 is what I need to pass into it. Okay. -1, because that's the lower left X, lower left Y, upper right X, upper right Y. Now let's go ahead and turtle. We're gonna, and just to show you what I'm doing graphically, what that does, Bob is equal to turtle dot turtle, right? The magical phrase to make a turtle. And now I'm going to say Bob dot go to X is equal to 1, Y is equal to 0. And save and run. Module turtle has no coordinates. Okay. So in other words, I need to do screen. How do I do that? How do I get my screen? How do I get this? How do I get my window? That's the only part I have to figure out. It's not turtle. I need to do turtle dot. I have to get the window to do it, which is annoying. Turtle screen instance called screen. So, okay, and then do I just do turtle? How do I get that? Turtle dot. Turtle dot screen. Or should I do turtle dot win? Window. Yep, okay. Win is equal to turtle dot screen. And then win, let's see, is equal to set world coordinates. Okay, has no attribute screen, which probably means it was capitalized. There we go. So I told him to go to 0, 1. So this square that we have here at the bottom now matches this over here. Does that make sense? It's 1, 1. So here I will show. Turtle, go to 1, 1. So Bob, go to 1, 1. Then go to -1, 0, and then go to -1, -1. Run it. So it went to 1, 1. Sorry, it went to 0. It went to 1, 0. Then it went to 1, 1. Then it went to -1, 0. And then finally -1, -1. It's hard to tell, but the line is a bit thicker on the edge. Now, we could do that. We might be able to make it easier by saying bob.color is red. Let's go ahead and see if that helps change his color. Yep, much easier to see now. That is path. So we can see that this is a square of where basically of size 2. It's a square of size 2 now, which means we can have a circle inside of it, right? So, but we don't actually need to draw the circle. Simply put, we will be able to know what we're going to do is that we're going to basically toss this turtle at different locations. We're going to tell this turtle to go to different random locations. For instance, like, and we do that by doing this for in range. So we're going to do this 5 times. Bob dot pen up to raise his pen. Okay. Tell him to raise his pen. And then what we're going to do is we're going to tell him to go to What I'm going to do is I'm going to import random now. And now I have to generate a random X variable and a random Y variable. So again, what I'll do is I'll look at random and see, okay, I know I've got rand int, okay. And that gives me a random integer between 2 points. But what about a random float? Okay. And so what about a random float? Random shuffle, real value distribution. So random.random gives us the most general random number, which is 0.0 to up to 0.1, not including, sorry, 0.0 to 1.0. For those of you who care, that's technically an infinite number of numbers between these points. But what we're looking for here is random.uniform. And I know that because I just read this. Return a random floating point number n such that n is between a and b. Okay. And it just simply says, hey, you can just figure this out by doing this equation instead. So it uses this to calculate this, but that's math, and I want to do less of that. So what I'm going to do is I'm going to say, hey, please generate. So X is equal to random.uniform -1 to 1, and the same thing for Y. Y is equal to random.uniform -1 to 1. And as you can see by the fact that I have to look these up, these aren't, commands I use too often, but I know that this functionality exists. So what I'm going to do is I'm going to say, Bob, go to that point. And now, because I'm not actually like leaving any, so here's the thing, Bob isn't actually like, he's got his pen up, so he's not actually going to this point. So what I'm going to do is I'm saying, okay, Bob.stamp. Okay. So error, bad input on line 13. What did I do? What did I do on line 13? I forgot the colon. So now what I've got here is, hey, import these things. We've created Bob. Told him to put his pen up, and then we generated 5 random points. And as you can see, we've got random. He's traveled to 5 random points on this grid. And if I could make him do as many as I need to, like 100. You can see he's just simply going to these random points over here and doing that. But this doesn't really tell me much. So what I'm going to do is I'm going to color. I'm going to color him based off of what he lands on. And what I'm going to do is that if he's landing in our circle, I'm going to color him red. Otherwise, I'm going to color him blue. But how do I know if he's landing in our circle or not? Well, we avoided using math for a while, but now it's just unavoidable. We have to use math. Okay. So we know that basically that this is a radius 1, right? So we know that since this all is centered on 0, 0, and this has this circle has a radius 1, right? That if I throw a dart, okay, if I throw a dart and its distance to the center is less than 1, then it's inside the circle. Does that make sense? If its distance to the center is less than 1, then we're inside the circle. Otherwise, if it's greater than 1, we are outside the circle, right? Does that make sense to everybody? So now, for those of you who forget, the distance equation in the Euclidean in Euclidean space is the square root of x squared plus y squared. So let's go ahead and just simply calculate that. So we need to import one more function. We need to import one more library. We have to import math. Yeah, I know, it's so dreaded. Okay, so distance is equal to math dot square root of x squared plus y squared, right? And that's the distance, the square root of x squared plus y squared. All right, as for y, please refer to, college algebra. But that's our distance in Euclidean space. That is the way it works. Okay. Now what we'll do is we'll say if distance is less than, or we'll go with equal to 1, then Bob dot color is going to be red, else Bob dot color is going to be blue. And I like this part is fun because we start seeing that we get colors going on over here. I'll run it again. So now if he's inside this circle, we get red, and if he's outside, we get blue. But this goes pretty slowly. To throw 100 darts, right? We were doing 10,000 games earlier. But this goes a bit slowly right now. So the idea here is now that, so it says, so I'm going to go ahead and copy this. I hit share code. Still having issues with that. I will send it out all as an announcement later today. Okay. So now that we have the animation working, we can add in counting and make a calculation. You can speed up. And so what's saying is that we can speed up the animation by using this tracer, which says that it skips drawings a number of updates and to wait for a certain number of milliseconds. So what we're going to do here is just follow it directly. It says use tracer 1225. Bob dot tracer is equal to 12 and 25, and that basically enables it to, basically it's not going to draw every movement the turtle does. It's only going to draw, as you can see, just a couple of updates after it does a couple commands. And what that does is that means it generates a lot faster. And if it generates a lot faster, that means we can push the number up. So now we do 1,000. And we can now clearly see that there's a circle, right? There's clearly a circle inside there. So let's go ahead and push that up to 10,000. And we'll go ahead and up the amount of tracer. And we can, very clearly now see that there was that we have a circle in here. Time limit, program exceeded time, runtime limit. That's okay. So only pause. So does this happen? Does it go? There we go. There we go. So 120 every 20, do 120 of these every 25 milliseconds. And there we go. We've got ourselves a circle inside there. Does that make sense? Like what I've been doing is just simply, all I'm doing is coloring the turtle based on whether or not he's in a circle. So if the turtle is less than 1 Euclidean distance from the center, he's red. Otherwise, he's blue. Okay. So all I did was just simply calculate the distance function, figure out how far he was from the center, which is, and the distance square is x squared, sorry, the square root of x squared plus y squared. where X and Y are where the turtle is. And then I just simply use that to figure out, hey, are you inside a circle or outside? And so now we can actually do our calculation, which is that what we're going to do is we're going to say hits is equal to 0. Hits is equal to 0. Trials is equal to 10,000. I'll do trials here instead, so I don't accidentally, so I can just change it in one place. If it's red, if its distance is less than 1, then that means we were inside the dartboard, so that's a hit. Hit is equal plus equal 1. And so now what I can do is I can now say, hey, print pi equals, and then I can do hits divided by trials. That's going to give me pi over 4, if you remember. So I'm going to multiply by 4. And order of operations will ensure that that's okay. And so now we run it, and it says pi is equal to 3.142. You like the Leibniz approximation. This approximation takes a lot of things to get correct. For instance, if I simply go down to 100 trials, I get 3.48 as pi, right? But the idea here is that the more we do, then the closer it's a 3.14159 I'm going to get. And as you can see, it's a bit jagged because that's what the shape of the turtle is, because the shape of the turtle is jagged. It's just an arrow right now. Make sense? So that's why our circle's a bit jagged. You can kind of see it over here. If we zoom in, like here is where a dart got thrown and only got partially overwrote by a red dart. Make sense? That's why it's going to look a bit jagged. Let's see, what kind of shape can I make the turtle? Shape. So let's see if there's a better one I can do. Could make him a circle. Set shape. Yeah, we could do. Yeah, turtle dot shape is circle. And sorry, keep forgetting, right, it's in this window. Turtle dot, okay, Bob dot shape circle. And now that should end up being a bit, oh, that was a bit worse. Oh, well. Now it's kind of groovy. So there we go. So as they said, around 1,000 or 2,000 repetitions will get you 3.1. And I did 100,000, which got me 3.14284, which is, I mean, it's got 3.14. So there, or at least at like when we first learned about pi. But yeah, that is a this too is a Monte Carlo approximation. I could make the turtle smaller, but I've spent quite a bit of time on this problem as it is. So these are basically Monte Carlo approximations. This is a fun little exercise we could do with turtles. And so we have 14 minutes left. So I think I'm going to leave us with the idea for our for a couple. I'm going to go ahead and tell you what the games we are going to simulate on Tuesday are going to be. Okay. Sorry, on Thursday, the games we're going to simulate. These are scam games, so they look like they're going to be fair, but they're not. Okay. So I'm going to leave you with these to think about. So game number 1 is as follows. We have, let's take from a deck of cards. Okay. We're going to take, let's see, 2 red cards and 5 black cards. Okay, so we've got 7 cards here. 2 red, I think it's 2 red and 5. Yeah, I think it's 2 red and 5 black cards. Got 2 reds and 5 black cards. Okay. And what I'm going to do is I'm going to flip them over so you don't know which cards are red and which is black, right? Because in your standard 52 deck of cards, you've got half the cards are either diamonds or hearts, which are red, or clubs and spades, which are black colored, right? So take 2 of the red, 5 of the black. We're going to shuffle them up. And your objective is that as the person playing this game is that I will pay you even money if you can flip over 3 of these cards without flipping over a red one. So I've shuffled these cards. So now we've got 1, 2, 3, 4, 5, 6, 7 cards over here. I'm going to ask you, hey, flip over 3 of these cards and I'll pay you even money. So if you flip over 3 of them and none of them are red, you get $1 or $5 or whatever you're playing for. But if you flip over a red card, I get $1. Make sense? Does that make sense to everybody? The objective of the game? So, and now he'll say typically, like, I mean, there's only 2 red cards there, you know, and so like your first flip, right, you got a 5 and 7 of succeeding. Your second flip, 4 and 6 of succeeding. And your third flip is 3 and 5. Each of those is better than 50% odds. So your chances of winning are better than 50%. Right? Yeah, that part was the lie. So that those are not the actual odds because those odds are not independent. They are dependent on each other. So the so there's that issue there. Okay. So what we're going to do is that I'd like you to think about the game and maybe if you're more statistically inclined, figure out the objective, you know, figure out like figure out what the real odds of the game are. Okay. The second game is very, very similar. Rather than doing 7 cards, we're going to have 9 cards laid out in a 3x3 grid. Okay. 1, 2, 3. And again, 2 of these suckers are going to be red. Okay. 2 of these suckers are red. And the bet is, can you flip over 3 cards in a row so that none of them can you flip over only 3 cards, flip them over in a line, and none of the cards be red? So in other words, if you flip over 3 cards, you lose. If you flip over these cards, you lose. These cards, but if you do it this way or this way, you win. Right? And as you can see in this particular configuration, there's a lot more ways to lose than there are to win. So basically, can you flip over 3 cards in a row and only flip over black cards and 9 red cards? Right? And again, the grid is randomized, right? So you don't know where your black cards are going to be. You don't know where the red cards are going to be. Okay. That's another game. Another game that we could go over, which we'll probably have time for, is right. Coin flipping is fairly straightforward, right? You flip a coin, it lands heads or tails, right? So the bet is, and this one's made to people who are particularly inebriated, I would think, which is I bet you money, more than even money, right? So you win maybe $1.25 or something, or maybe $1.10. If you flip a coin 10 times and comes up with 5 heads and 5 tails. Okay, so flip a coin 10 times and end up with 5 heads and 5 tails. Doesn't matter what order they come in. You just got to get 5 heads and 5 tails. Make sense? Now that's a classical Bernoulli trial, where basically, and again, that's a uniform distribution, where basically you've only got like a 30% chance of winning that. But again, try figuring out the actual odds for that game. These are games, the idea behind this are games that sound fair, but they're not. And I've got a lot of these. These are quite fun because they get you thinking. So there's a number of games like these. So that's what we'll be doing next class. And on Thursday, sorry, we'll be doing that on next class. And then let's see on our calendar. So I'll go over that and maybe probably try to do go over GitHub on Thursday as well. So I may only have time for one of those games to make sure I go over GitHub before the lab, just to give you an idea of what the GitHub is. And then we'll do a bit more of Monte Carlo and explaining about what the final project is next week. And then on the actual week of April, we'll start talking about final project as well as regular expressions. But after the pig homework, you will not have any more mandatory homeworks. All that will be left is the final project. So yeah, all right, take it easy, and I will share this code. Announcements. Stop sharing. Yep, give me a second. And stop.